picking up where we left off in the last video. I apologize for kind of cutting off, right at the end fairly abruptly and quickly. So we're going to go back, relook at the aquifers first, and then move on to the next part. So as we're getting this irrigation water, again, we're tapping in the aquifers to get the majority of our irrigation. Most of the places that we farm don't have big lakes around, don't have access to rivers that they can pull from, and even if they would pull from rivers, it's not the best option because, again, most of the big rivers we need for transportation, things like that. So it's kind of limited in how much water we can pull from those. So when we look at our irrigation water, we tend to pull from aquifers. And again, there was two different kinds. There was confined and unconfined. Confined aquifers are going to be sandwiched in between two impermeable layers, whether it's two layers of bedrock or bedrock and clay. What can't happen whenever you have the two impermeable layers is the water is unable to penetrate through that layer. So there's no recharge of these confined aquifers, making them non-renewable. Now, the good news is our irrigation water doesn't come from these non-renewable aquifers. Instead, we drill down in to the unconfined aquifers. The unconfined aquifers is that water that's underground, but not super, super deep, fairly easy to access. And the good news is it recharges readily as the water percolates downward, permeates into the ground, and then percolates downward. As that water percolates downward through the soil too, it's going to naturally filter it and prevent pollution from finding its way into those aquifers, which is good for us because it's a great source of fresh water. Most of our drinking water comes from these unconfined aquifers underground. Again, these are both examples of groundwater, not surface water. So when we look at the groundwater supplies, we're always looking at what level the water table's at. The water table is the upper layer of this saturated zone. So all of this is the aquifer. The water table is that very, very topmost layer of it. And that depth is going to fluctuate with time based on rainfall, based on snow melt, drought, all those different conditions. But the overall thing that we do is we drill wells down into it. If we drill wells down into the unconfined aquifer, then we need to use pumps to get that water up to the surface. Sometimes, not all the time, but sometimes, if we drill a well down into a confined aquifer, sometimes that water is pressurized and it naturally forces its way up our wells, and we don't have to use pumps at first until we take too much water out of that confined aquifer. Then eventually we'll have to use pumps. But pretty much every time, every situation we have, consider every time you use a well, you're going to be using a pump to get them to the surface. Now, when we're using pumps, we're also using fossil fuel energy to get that electricity needed to power the pump. So anytime we're using water from these confined or unconfined aquifers, always associate that with pumping, with electricity usage, and inevitably burning fossil fuels to get that electricity usage, unless you're using renewables, which we'll get into the next unit. So we left off talking about the Ogallala, I can never pronounce it right, Ogallala aquifer. All right, that aquifer, again, spans 9 different states throughout the United States. We're not equally using the water within those states either. So some states are over-consuming, some states are being harmed by that overconsumption. So when we look at the depth with time, we see that the uppermost part is filling up and it has more water in it than what it used to have. The bottom part, though, is the area of concern. That's where we're starting to see the water reduce, and we're losing water faster than it's being replaced. We're using water rather faster than it can be replaced. So our overall depth of that aquifer is decreasing. That's problematic to us because, again, this is our grain belt where we're growing most of our agricultural crops. When we look west of the Mississippi, you have the Ohio River running down through here, the Mississippi, so on, like this. All those little feeder rivers, the tributaries to it, are feeding into that Mississippi. All of this area here is our grain belt. We originally started to use this area as our grain belt because of the river system we have. Once we got the technology to be able to tap into this aquifer, that's when we really start to expand that grain production, because now we have the ability to use irrigation and to turn areas that used to be too arid to grow, now we turn it into productive farmland. So, once this aquifer is gone, we're going to lose the majority of that farmland just because we don't have the water necessary to keep up with our large-scale agribusiness anymore. And then again, when we look at the aquifer, we should be protecting this, but again, linking into the next unit, when we talk about energy sources, we're trying to find ways to get those energy sources to and from certain areas in an efficient and cost-effective way. One of the ways they plan to do this was with the Keystone XL pipeline and the Dakota Access pipeline. When we look at the Keystone XL and Dakota Access pipelines, the Keystone XL, for instance, is going to go straight through this aquifer. So the current pipeline kind of goes off to the side here, and it only feeds, up into Illinois and over into Oklahoma. We need to get it a little bit further down here into Port Arthur and into parts of Texas, because we need, the ease of transportation. That's where most of our shipping industry main ports for shipping come in. So that's where these huge oil tankers can fill up very easily. It's kind of hard for them to get up and down the Mississippi River, but that's why they took it into Illinois, because you do have the Mississippi River right there. That is a mode of transport of this oil up and down using waterways. But regardless of whether we're looking at the transportation down here, the big scary part of it is the proposed pipeline change is going to take it straight down through the Ogallala aquifer. When it does that, now we have the potential for contamination and leaks, and then the potential pollution of that aquifer. If we pollute that aquifer, people are going to lose their freshwater drinking sources, they're going to lose their irrigation sources, all of those. So that could spell inevitable disaster for our grain belt. It's not going to run through the water, of course, but even if it's running over the surface, that's still going to have that potential. If there's a leak there, drain down into that aquifer. The soil can only filter so much. Right. So our next part of the green revolution. So far, we've talked about using alternative farming practices. We talked about mechanization. We talked about irrigation. Now we're going to get into our use of fertilizers. When we started into the green revolution, this was our first use of the synthetic fertilizer. We've been using fertilizers for ages. The main one being manure. That's our organic fertilizer. We have manure, we have compost, anything that's a partially decomposed or completely decomposed material from plants and animals, that organic material. This is going to be high in nutrients, but it's not tailored specific to a type of nutrient. You're getting more of a generalized nutrition here. When we look at synthetic fertilizers, now we're able to produce them, in a lab setting, and we're able to produce specific nutrients. So produce specific ratios of nutrients, I should say. And again, that's going to be important, because when we look at our agricultural crops, some of them are going to consume very specific nutrients in higher quantities than other nutrients. So adding organic fertilizer doesn't really help us out as much, because it is going to replace nutrients, but also going to put in all the nutrients as opposed to just the ones we need. So we have over-application problems where that fertilizer can then run off into the bodies of water, cause the eutrophication process, all those things. We can still have that problem with synthetic fertilizers, but now we can tailor it more specific to the crops we're growing. This allowed us to monocrop. And the reason why it allowed us to monocrop, we don't have to crop rotate anymore. We don't have to worry about leaving fields rest for a few years, because we've already consumed all the nitrogen in the soil. Now we need to plant crops that are going to put nitrogen back in. We don't have to do that anymore. We can grow the same crop year after year after year on the same plot of land, because we can put synthetic fertilizers into the ground to replace the nutrients. Now, there are drawbacks to them. We'll talk about the drawbacks here in a second. But the benefits, that's allowed us to increase our yields considerably by using these synthetic fertilizers. When we look at synthetic fertilizers, we tend to focus on the macronutrients: nitrogen, phosphorus, potassium. Main form of nitrogen that we need, again, are the nitrates. Main form of phosphorus that we need are the phosphates. And again, potassium is element K. So when we look at these are the ones we need in high amounts. Most of the time we don't add nitrates themselves, we'll add ammonia. And you'll use big tanks of anhydrous ammonia on fields a lot of times and put that ammonia right into the soil. The thought is the ammonia, once it hits water, is going to change to ammonium ions. Those ammonium ions are going to be converted by bacteria into nitrites first, NO2 first, then further into nitrates through the bacteria. And again, you should remember that that's the nitrogen cycle. We have that ammonification, then nitrification, and so on, all those different processes that happen. If you don't remember this process and the names of the steps, make sure you're using those nitrogen cycle flip charts we made, and make sure you guys know that stuff. You guys need to know those chemical cycles really well. The This one helps us out considerably. But the phosphate in synthetic fertilizers is the huge help that we have because, again, phosphates are linked into the phosphorus cycle. It's the slowest of our biogeochemical cycles. We were dependent on rocks weathering to release our phosphates that we needed for agriculture before. Now we can add those phosphates very quickly because we can synthetically produce those phosphates and incorporate them into these synthetic fertilizers. We can crush up rock, extract the phosphates from the rock, and incorporate those into these NPK fertilizers and quickly put those phosphates back in the soil, as opposed to putting manure, which is going to put phosphates in, but not necessarily in a high enough quantity. What we can do with the NPK numbers is we can tailor the fertilizer specific to what we need. So say we're using a 5-5-5 fertilizer. That means it's going to be 5% nitrogen, 5% phosphorus, 5% potassium. That would be if we need a general application. Say that we have a crop that's using high amounts of potassium, but not really nitrogen or phosphorus. Now we can do a 0-0-20 for potassium. That means that of that fertilizer, 20% of it is going to be potassium. There's no nitrogen, no phosphorus in it. So we can, again, replace the nutrients that are needed for the specific crops. This is what allowed us, again, to monocrop with it. I'm going to go backwards here for a second because I didn't put the slide in that I meant to put in. When we look at the synthetic fertilizers, one of the big drawbacks is that it's a heavy fossil fuel consumer. The production of them require huge amounts of fossil fuels to make these different fertilizers because, again, it's energy intensive process. And anytime we're using fossil fuels, again, link it back to greenhouse gases. We have lots of carbon dioxide being produced. We're going to have lots of methane problems with it as well, because a lot of times we're burning the methane to produce these fossil fuels, or not to produce fossil, sorry, produce these fertilizers. So some of that methane may find its way and leak out and get back up into the sky. But probably the biggest impact of these synthetic fertilizers is the nitrous oxide production that happens. That nitrous oxide production is almost 300 times the heat holding capacity of the carbon dioxide. So when we look at it in terms of this, carbon dioxide we know is bad from a heat holding capacity. Methane is about 25 times as bad as carbon dioxide, and nitrous oxide is about 300 times. This is one of the biggest producers. Synthetic fertilizers and synthetic pesticides, one of the biggest producers of nitrous oxide worldwide. And again, we don't produce huge quantities of it, but even at a small quantity, it's still going to be majorly impactful. And again, it's due to the fact that we need huge amounts of fossil fuel energy to make these fertilizers. We're having to force a reaction to happen. So to do that, we're putting energy into the system. The other thing that we were able to start doing with the Green Revolution was using pesticides. The difference between pesticides and fertilizers, and this is a hugely important thing, fertilizers are designed to grow and help grow. Pesticides are designed to kill and do kill. So pesticides didn't increase yields by helping things grow. They increased yields by killing pests. So they increased the yield by reducing loss. So when we look at the crop loss that we have, any farmer is going to tell you they're going to lose a certain portion of their field to pests. Even if you're using pesticides, you're never going to kill 100% of the pests. So we're going to have weeds, for instance, outcompeting the plants for sunlight, water, nutrients. We're going to have insects come in and eat the plants. So we're going to lose a certain portion of our crop every single year to loss from pests. By using pesticides, though, we're going to reduce that loss, which is going to increase our yield. When we use fertilizer, we're increasing our yield by allowing things to grow better. That's the big difference between it. And again, they weren't very creative in how they started naming these pesticides. It's based off of which pest they're looking at. Insecticides kill insects. Herbicides kill herbs or weeds. So again, know that these are going to be the weed killers. All right, and then when we look at the other ones, we have rodenticides, or rodenticides, however you want to pronounce it. We have fungicides. Rodents are designed to kill rodenticides. Rodenticides rather are designed to kill rodents. Fungicides or fungicides are designed to kill fungi. But again, the big thing with them, they're going to increase our yields, not by helping the plants to grow better. They're going to reduce the loss because now we don't have those pests out competing our agricultural crops. Now, when we look at the pesticides too, we have two different categories of them. We have broad spectrum and selective pesticides. I always use the analogy of weapons in armies. So when we look at the broad spectrum, these are the grenades. And grenades are designed to kill everything in its path. You drop the grenade here, but it's going to kill everything in that blast radius. So everything within here is going to die. That's the same thing with a broad spectrum pesticide. You apply it to the field knowing it's probably going to kill everything in that field. It's going to kill the beneficial organisms and the harmful organisms alike. So that's an important part to put here. So the beneficial and harmful are both killed. So when we look at these beneficial organisms are mostly our pollinators. So, or it could be something like a snake. A snake is going to eat the rodents that might potentially kill off the plants. It could be bats that it's killing, or the insects that the bats eat. Those insects may not necessarily be harming the plant, but if we're putting on a broad spectrum agent, it's going to kill all the insects in the field. So now those pollinators are killed also, the bees, the butterflies, things like that. In addition to it, the animals that depend on those pollinators or other beneficial insects aren't going to have their food source. The bats do a great deal of beneficial crop control or pest control for us. So we should be providing food sources for those bats to encourage them to be there. That would reduce our pesticide usage. But as we use more of these broad spectrums, we're going to kill off all of those beneficial and harmful organisms both. So what we should turn to is more the sniper rifle approach. And the sniper rifle targets a specific organism. It's going to take and only hurt, a type of organism or a range or class of organisms. So let's say that your field is being attacked by aphids, and aphids are just a tiny little flying insect. So when we have those aphids coming in, they could decimate the field. We want to kill those off, but leave everything else behind. We want to leave the beneficial bacteria in the soil. We want to keep the other insects that the bats might be eating, or the other insects that may be pollinating. So we use an aphid selective pesticide, where it's only going to hurt the aphids, it's going to leave everything else. The other thing we have to look at when we use pesticides is the persistence of them. Persistence is how long it remains deadly in the environment. So, we're looking for how long it's going to stay deadly. Right? Ideally, we want to use a non-persistent selective pesticide. Those are the ones that break down fairly quickly after the application and then are selective to only one group of organisms. Because what we don't want to do is have that pesticide build up in concentration over time. If it remains deadly for, say, 20 years, every time I apply it, I have last year's residue left over. So I'm adding it in a certain low concentration, but each year that amount of that deadly pesticide in the environment is going to increase each year. And we saw this with our first pesticide that we had, which was DDT. DDT was that first commercial inorganic pesticide. The one we've always used organic pesticides throughout time. We used the extracts from the tobacco plants that killed off certain insects. But then when we found DDT, it was this miracle chemical that was designed to kill all these problemsome pests. And when we applied it, we thought, oh, great, it's doing a great job. It's reducing our crop loss. We're seeing our yields go way up. But what we didn't realize was it was bioaccumulating in the tissues of living organisms because it had a very high persistence. And bioaccumulation is when an organism, say we'll make it into a bird. Say the bird is eating insects that are exposed to that DDT pesticide. That bird is going to accumulate more and more of that DDT because it has a high persistence. So each time it eats, it's eating more and more and accumulating more and more of that DDT. So it might start out with a concentration of 0, but then through a few years of feeding, that bird might come up with, say, 1.8 parts per million. And again, I'm just making up numbers, but again, it's going to accumulate a huge quantity of this pesticide in its individual tissue. That then can get to the point where it's toxic to the bird and the bird ends up dying from it. Right? The other thing that happens is we see not only bioaccumulation is where it accumulates in the individual tissues of an individual organism, but we also see biomagnification. And biomagnification is going through the steps of the food chain. So we apply it to the water, for instance. Pesticide gets in the water. The plants then absorb that into their tissue. Those are our producers. They're going to have a low concentration. They're going to bioaccumulate a small amount of that pesticide in their tissue. But then let's say a grasshopper eats the plants. right? Only 10% of the energy transfers, so it has to eat a huge quantity of the plants to survive. So now it's going to accumulate even more of that pesticide in its tissues. Again, bioaccumulation at the individual level, it's biomagnifying through the food chain. Then we're going to have a bird eat the grasshopper, and that bird is eating a grasshopper that has 2 parts per million that's accumulated in its tissue. The bird's only getting 10% of the energy, has to eat a huge quantity of it, so now it might be up to a 7 parts per million concentration. So you can see the concentration of the pesticide grows quickly with time. So we have to be very careful with the agents that we pick so that they're not only going to break down very quickly and not be persistent, but also that they're narrow spectrum or selective. Because what happens is not only do we have that bioaccumulation and biomagnification process, but we have something called pesticide resistance that springs up. And pesticide resistance is very similar to antibiotic resistance. So you have a crop that's infested with pests. So we apply the pesticide to the field. Most of the pests are going to die. The resistant ones survive. So we reapply that pesticide, but it doesn't reduce our crop loss any because those insects are now resistant to it. There's always going to be a certain portion of the population that's resistant to any pesticide that we put or any antibiotic we expose them to. So again, non-resistant ones die off, resistant ones survive. We reapply the pesticide, but there's no benefit to it because, again, they're resistant to it. So what we should be doing is alternating the pesticides we use. To avoid this pesticide treadmill, we apply pesticide A, for instance. The ones that are immune to A survive. So the next time we apply, instead of applying pesticide A again, we have 2 options. We can either apply it in a greater concentration, or the better way to do it is to apply a different pesticide. Now when we do that, these ones that are resistant to A are exposed to it. The resistant A ones die off, the B resistant ones survive. Right? Then again, we reapply A, that kills off the A or the B resistant. When we reapply B, it kills off the B resistant, or sorry, the A resistant ones. This way, what we see is our pest population stays fairly steady and stagnant. When we look at the pesticide treadmill, what we end up with is population versus time. And we see a really unique thing that happens. We have pest population increasing, so we get to the point where we have to apply our pesticide. We apply it the first time. It kills off the majority of them, but the resistant ones survive and start to reproduce. Now crop loss is starting to increase again. We reapply the pesticide. It still kills off some of them because not all are going to be resistant. But when you see where the population dips to, it's a higher population than what it used to be. Now we get to where crop loss increases again. We reapply the pesticide. And we start to see a graph that kind of shows something like this. And again, what this is showing is each application of the pesticide becomes less and less effective. Our overall base population left over after each application is increasing each time. So what we do is, where you apply pesticide A, that brings the population down to here. When it goes up again, now we're going to apply pesticide B, and pesticide B brings it back down to the baseline. Grows up again, reapply a different pesticide, and what we end up seeing is our base population of insects or pests of any kind is going to be fairly steady and stable. So this alternating of pesticides is the better way to do it. When we keep with the same pesticide, we end up building up resistance and our pest population grows even though we're applying, a lot of pesticide each time. Okay, our next video then will deal with genetic engineering. Hopefully you guys understood the pesticides. If you don't, please come in and ask, and I'll gladly run through everything with you.